These are the frequently asked questions for pre-calculus for section 7.4, day 2. And this group says, use an algebraic method in exercises 21 to 32 to find a partial fraction decomposition. So the first thing we need to do with number 26 is we need to factor that denominator. And that starts by pulling out any common monomial factors. And there is an x in both of those. And once you get that out, hopefully you notice that that is a perfect square trinomial. So now we have an x and an x minus 3 squared in our denominator. And what we're going to have to do is use a over x plus b over x minus 3 plus c over x minus 3 squared. We don't need any linear numerators because we do not have any irreducible quadratics. That x squared minus 6x plus 9, we reduced that already, so that's taken care of. And then we work as though we were trying to get a common denominator of x times x minus 3 squared. Our first term with the a would require the x minus 3 squared. The b term is going to need an x and one x minus 3. And the c term just needs an x. That's all it needs. Now we go back and we expand our x minus 3 squared and probably distribute our x at the same time while we're at it. And then we have to distribute our a and b so that we can see what's going to happen with all of the terms. So let's pull it all together. We look back and say, okay, here's our x squareds. We have ax squared plus bx squared, and that has to equal, well, in the original, our numerator, we didn't have any x squared, so that has to come out to be 0. So those are taken care of. Now we need our x terms, negative 6ax minus 3bx plus cx. And we go back and look at the original and see that we had a negative 6x for the x terms. And last but not least, we have a little 9a, and that has to come out to be, in this one with a numerator of negative 6x plus 25, that's going to have to be 25. Now, if we take the variables out, which is usually what we want to do with these, this will say a plus b equals 0, negative 6a minus 3b plus c equals negative 6, and 9a equals 25. So there's an obvious place to go to start solving this algebraically, and that's the 9a equals 25. Unfortunately, this one is going to give us some nasty fractions. We do know that a plus b has to equal 0, so a and b have to be inverses of each other, which means b would be a negative 25 ninths. But yeah, we're going to have to do some work with the other equation in order to get our c value here. So we have negative 6 times our 25 ninths minus 3 times our negative 25 ninths plus c equals negative 6. This would give us a negative 150 ninths, and this will give us 75 ninths, and that's going to be plus because we had minus and negative, plus c equals negative 6. So negative 75 ninths plus c equals negative 6, which is really negative 54 ninths. And we would add 75 ninths to both sides. So this one's just putsy. You know, there's a lot to take care of there. And then negative 54 ninths plus 75 ninths will give us 21 ninths, which is going to reduce to 7/3. So there's our A, B, and C. And we go back to figure out, okay, what did we use here again? So our A needs to go over the x, our b over x minus 3, and our c over x minus 3 squared, and we will have this partial fraction decomposition done here. So 25 ninths over x plus negative 25 ninths over x minus 3 plus c 7/3 over x minus 3 squared. And that is how we want you to write this, and that's so that we can look at this easily and see that you found your A, B, and C, and everything is just glaring at us. You know, we don't want to do any more work with this that would mess up the fact that we can see your A, B, and C right there, glaring at us. All right, then number 28. Well, again, we have to factor the denominator, and this one, if you take an x squared out, works out really, really nice. So we have that little x plus 4. So now when we expand this to think about that partial fraction decomposition, we need a over x, b over x squared, because we need each power. Remember, when we build up fractions, we need the highest power of whatever we see as part of our LCD. And then c will be over x plus 4. We do not have any irreducible quadratics, everything factored nicely, so we can just get busy here trying to get this LCD. Our a over the x would need another x, and it will need an x plus 4. Our b, that's going to need an x plus 4. And our c, well, that's just going to need the x squared. Oh, that almost looks like parentheses, though. I better make that a little bit more defined. There we go. So now we go ahead and distribute the x. And then we'll distribute everything else. All of our variables. So we have ax squared plus 4ax plus bx plus 4b plus cx squared, and our x squared terms come together. So we have ax squared plus cx squared, and that has to equal our 5x squared. Then we have our 4ax plus bx, and that has to come out to be 7x. And we have a lovely little 4b, which has to equal a -4, because that was our original numerator, 5x squared plus 7x minus 4. So again, obvious here where we're going to do the algebra, but let's get the x's and x squareds out of this equation because we don't need them anymore. Top one, a plus c equals 5. Middle one, 4a plus b equals 7. And the bottom one, 4b equals -4. So 4b equals -4, pretty obviously b is going to be -1. And then we'll go back to the middle equation and say, well, 4a plus our -1 has to come out to 7. So 4a has to equal 8, and that means that a is 2. And then we'll go back to the top red equation there, and we will put a 2 in for a. And c will equal 3. So there is our a, b, and c right there. And we had them in order: a over x plus b over x squared plus c over our x plus 4. So there is our answer: 2 over x plus -1 over x squared plus 3 over x plus 4. Next one, number 30. Well, the good news about 30 is it's already in a reduced factored form down here, x squared plus 2 squared. The problem is that it is an irreducible quadratic. We have x squared plus 2, which is not factorable. So we're going to need linear numerators on both of these. We're going to need an x squared plus 2, and then a cx plus d over an x squared plus 2 squared. And these tend to look more intimidating than they really are, because remember, our LCD here is just x squared plus 2 squared. So our first numerator, ax plus b, our first fraction, numerator and denominator, would just need one more x squared plus 2, and even better yet, our cx plus d doesn't need anything. It already has the least common denominator. So a little awkward FOIL in the front: ax to the third plus 2ax plus 2bx squared plus 2b plus cx plus d. So ax plus x squared, ax to the third, ax and 2, 2ax, b and x squared would give us, oh, not 2bx squared, that'd just be bx squared. And then last times last is the 2b. All right, we have ax cubed. That is the only cubed term, which is great. That certainly makes this a lot easier because that has to come out to our 3x cubed. We have only one x squared term. Again, that's fantastic. It's the only one we have. In fact, we don't see one in our numerator up there. So bx squared equals 0 tells us that b equals 0. And then we have 2ax plus cx, and that has to equal 6x. And then we have d, no other constant. That's going to have to be the -1 from our numerator. So far, we know a equals 3, b equals 0, 2a plus c equals 6, and d equals -1. So we're almost done. All we have to do is figure out c. So 2 times 3 plus c equals 6 using this equation. 6 plus c equals 6. Well, that means c is 0. So we have a of 3, b of 0, c as 0, and d of -1. And it was ax plus b, so 3x plus 0 will just be 3x over x squared plus 2 plus, and then we have cx plus d, but c is 0, so it's just going to be d over x squared plus 2 squared. So that is our partial fraction decomposition right there of 3x to the third plus 6x minus 1 over x squared plus 2 squared. Number 32 is a little monster. We have 2x squared minus 4x plus 3, but our denominator is a sum of 2 cubes, and the sum of 2 cubes factors into a plus b times a squared minus ab plus b squared. So we need to get that factored correctly. And a is x and b is 1. So this will be x plus 1 times x squared minus 1x plus 1. And then we try to find if we could factor x squared minus x plus 1, but there aren't two numbers that multiply to 1 and add to -1. So that is as far as we can go with factoring, which gives us an irreducible quadratic. So we will have an a over x plus 1, but we're going to have a bx plus c over x squared minus x plus 1. This is our LCD. So we build them up, and that means a means x squared minus x plus 1, which seems really bad, but we're just going to distribute an a. And then we have our bx plus c, which is going to need an x plus 1. So ax squared minus ax plus a plus, again with the awkward FOIL here, bx squared plus bx plus cx plus c. Now let's see what we have. Ax squared plus bx squared. That has to come out to 2x squared from our numerator. And then our x terms, negative ax plus bx plus cx has to equal a negative 4x, again, looking at that numerator. And then a plus c has to equal 3. So away we go. Let's take those variables out of there. A plus b equals 2. Negative a plus b plus c equals negative 4. And a plus c equals 3. So I looked at this one and thought, how am I going to get all of this figured out with just the one major equation that has all 3 variables in it? And the easiest way to do that is to say, you know what, I'm going to substitute in for both of those in terms of a. So from the first equation, I'm going to get b equals 2 minus a. From the third equation, I'm going to get c equals 3 minus a. And then I'm going to substitute both of those into the middle one. So a plus 2 minus a, oh, sorry, it was a negative a, plus 2 minus a, plus 3 minus a equals negative 4. I'll obviously be able to get a here by just using substitution a couple of times. So negative a plus 2 minus a plus 3 minus a, dropping all the parentheses, will give us a negative 3a plus 5 equals negative 4. And then what we would do, it doesn't look much like a negative 4, let me get that in there, is subtract the 5, which ends up working very nicely. So we divide by the negative 3, and we get a is 3. Now that we have a, well, we can go back to both of these as a little shortcut to find b and c. So b equals 2 minus 3, which is negative 1, and c equals 3 minus 3, which is 0. So now let's put it all back together. We had a, which is 3, over x plus 1, plus, and then we had bx plus c, but c ended up being 0. So we go back and we see that our b value here was negative 1, so it's going to be negative x plus 0 over x squared. Oh, let's see, I better go back and look that one up. I think that was x squared minus x plus 1. From the sum of two cubes that we had way back up there. Yep, x squared minus x plus 1. So there we are. There's our partial fraction decomposition. So using substitution on that system, using substitution twice. Now 33 says use the division to write the rational function in the form q of x plus r of x over d of x, where the degree of r of x is less than the degree of d of x. Then find the partial fraction decomposition and compare the graphs of the rational function with the graphs of its terms in the partial fraction decomposition. Number 33 is we need to do the long division. So we have an x squared minus 1, and we need to match up that first term as a 2x squared. So we're going to have to multiply this by 2. That will give us 2x squared minus 2. So the 2 is doing its job. We're going to put that up there. But we have to remember that we really need to subtract. So we're going to change this to adding negatives, and we'll be able to get what we need. So this will give us x plus 5. And since we can't divide any further, that is our remainder over x squared minus 1. So far we have that f of x equals 2 plus x plus 5 over x squared minus 1. And now what we would need to do is our partial fraction decomposition of x plus 5 over x squared minus 1, but that's factorable. So we need to factor. That's going to make our life a lot easier. It's a difference of 2 squares. We have x minus 1 and x plus 1. So a over x minus 1 plus b over x plus 1 will get us what we need. And you need to focus on the fact that this is now our new numerator. So a times x plus 1 plus b times x minus 1, because we remember that this is going to build these fractions back up to where they will have a common denominator. And once they have a common denominator, we could actually put those together. All right, we will go ahead and distribute.
Reagan Mathis to the counseling office. Reagan Mathis to the counseling office.
Ax plus a plus bx minus b. And now we need to match that up with our x plus 5 for our numerator. So ax plus bx has to equal 1x, and then a minus b needs to equal our 5. So our two equations here, scoot this up a little bit, are a plus b equals 1 and a minus b equals 5. Most people at this point would just go ahead and use elimination and get a equals 3, and then put that back into either one of the equations. The top one, a plus b equals 1, looks pretty good. So 3 plus b equals 1. B is negative 2. So what we don't want to forget when we rewrite this is that we had a 3. Actually, we had 2 in the front of this one. And our decomposition gave us the a and the b that we needed over the x plus 1 and the x minus 1. So let's go back and see which one we used first. So A was over x minus 1. So it'll be 3 over x minus 1 plus, and then B is a negative 2 over x plus 1. So there is our partial fraction decomposition. Now what we have to do is take a look at this and figure out why are they having us look at this graphically? You know, what does this have to do with the cost of tea in China? Well, we talked about this in class, that the behavior at the asymptotes is what we're going to see from those fractions that we have after that 2. So if you graph the original, this is what you get. And you'll notice as you're looking at this, okay, what's going on here? Why do things look the way that they do? This branch behaves as this branch does. So that's 3 over x minus 1 that gives us that branch. And then as you look on the other side, this branch gives us this branch's behavior as it approaches that asymptote of x equals negative 1. So what we're seeing here is that we can get a really good idea of what the hyperbolic branches are going to be doing by our partial fraction decomposition. So that's what they want you to see, that's what they want you to sketch. You certainly could probably just use your graphing calculator, make those sketches on your paper, and notice what's going on with those branches. So I probably won't do that part for number 34. For number 34, I'm going to write your partial fraction decomposition for you. Again, we need to start with long division because we can. So we're going to take 3 times x squared minus 4. And it's working, it's doing what it needs to do. And then we're going to subtract. So 3x squared minus 3x squared is gone, but we have 2x plus 12 as our remainder. And that's what we're going to work towards with our partial fraction decomposition. But we have to notice that obviously we can factor that difference of 2 squares in its denominator. That's going to help us out a lot. So we're going to have a over x minus 2 plus b over x plus 2 do that partial fraction decomposition for us. The first fraction is going to mean an x plus 2. The second fraction is going to mean an x minus 2. This will give us ax plus 2a plus bx minus 2b. And ax plus bx has to equal 2x because that was our numerator. And then we have 2a minus 2b, and that needs to come out to 12 because that was our numerator. So, taking the variables out, we have a plus b equals 2, 2a minus 2b equals 12. Totally up to you how you want to solve this, whether or not it's going to be elimination or substitution. I think this time I'm going to multiply by negative 2.
Attention, science department meeting will be held in the principal.
So we have negative 2a minus 2b equals negative 4. A's are going to drop out. Negative 4b equals 8. And then b, of course, would give us a negative 2. And then we can go back up. We've got a plus b equals 2. And we know that b is negative 2. So we would add 2 to both sides, and we would get a 4. All right, so now we need to go back and look which denominator did we use for each. And a was over x minus 2. So we'll have the 4 over x minus 2 plus negative 2 over x plus 2. But we certainly are not going to forget that there was that 3 that we had achieved by long division in the front. And now the graphing part, I'm going to leave that to you because, again, what you're supposed to do is graph this and see the behavior at the vertical asymptote, graph this and see the behavior at the vertical asymptote, and then go all the way back up to the top where we had this, and graph to see, does all of this match up? You know, our 3x squared plus 2x over x squared minus 4. Not the whole graph, but what you'll see is that the behavior at the asymptotes is the same. So that's the graphing part I'll leave to you.